Okay, this is 1.5 example 1 where we actually find the sum of an infinite geometric series if we can. And I have that formula up there, but I want to add the condition for it. You can only use this sum to infinity if r is less than 1 or greater than -1, which really means the series is convergent. There's another way of writing that, which is that the absolute value of r is less than 1. So when this question asks, decide whether each infinite geometric series is convergent or divergent, it is convergent if the absolute value of r is less than 1, and divergent if the absolute value of r is greater than or equal to 1. Now, a lot of students will just remember that if the geometric series term by term is getting smaller and smaller and smaller, that means that the common ratio is, the absolute value of that is less than 1. Now, I would highly recommend, at least initially, that you check it. Every time you get an infinite geometric series, you should be finding the common ratio anyway. It's very rare that you don't need that common ratio. So if I look at A, I can take, and I'll write it, term 2 divided by term 1, or I'll write beside, we could take term 3 divided by term 2, because both of those things are equal to r. It's kind of a weird way of writing that, but I'm going to write first that -1/3, which is term 2 divided by 1, that gives me -1/3. I could also look at +1/9 divided by -1/3. I can rewrite that as the numerator times the reciprocal of the denominator, and I do still get -1/3. So I hope I hope we all agree that for A, the common ratio is equal to -1/3, which means it is convergent. Now, students do not like typically when the common ratio is negative, but that's fine. It's not a big deal. It just means that the terms are switching signs as we travel through, or I guess as we read through the series. We can still use our formula. We just have to make sure we're careful with the substitution. So I'm going to say that because it's convergent, we do have a sum to infinity, and that's going to be equal to the first term, which was +1, divided by 1 minus the common ratio. But the common ratio is -1/3, not just 1/3. And it's really important that whatever sign is on the common ratio, that needs to kind of carry with it into those formulas. All right, so that means that the sum to infinity is going to be 1 over. Now, in order to add fractions, I'm going to change the number 1 into 3/3, and then I'm going to add 1/3. I'm adding because I was initially subtracting a negative, and I get that the sum to infinity is equal to 1 over 4/3, which is the same thing as 1 times 3 over 4, and I get that 3 over 4 is the infinite sum. Now, what that means is that if we'd let that series just travel, or I guess write the numbers forever, for the rest of our lives, eventually, if we add all those together, we are going to get 0.75 exactly. Now, you can get a fraction, you can get a whole number, all bets are off. Please don't get taken, out of these problems. If you do get a fraction or something like that, they are not all going to be nice kind of natural number sums. Now, you'll probably notice I didn't leave myself a lot of room, and that's because B is divergent. Now, to show that it's divergent, which we're going to expect you to be able to do, I'll just maybe fit it in here in this red box. If I look at B, I can find the common ratio by taking -4 divided by 2, I get -2, or +8 divided by -4, I get -2. That means that the absolute value of R is greater than or equal to 1, so it's divergent. And really what that's saying is that if we looked at, the 10th sum, the 11th sum, the 12th sum, and we kept doing until maybe we had sum 100 or something like that, we would not notice, well, there'd be a pattern, but it wouldn't be approaching a number. Whereas if I looked at A and I took the sum at 1,000, the sum at 2,000, the sum at 3,000, we would notice that those sums are getting closer and closer and closer to 0.75. And I think language is important in math. That literally is what converges means. If we let that series keep going, then the value is going to converge on what we call the infinite sum. Whereas divergent, it diverges, right? It doesn't actually approach a number. It just keeps on getting larger and larger or more negative, or whatever the case is with that question. All right, just another example. This is, a bit of an afterthought in chapter 1, but it is a pretty important concept because we actually use this infinite geometric series concept to prove a couple calculus concepts in grade 12.